Welcome to The Explainer. Today, we're taking a heavily mathematical concept and transforming it into a highly practical tool to understand exactly why the Earth moves. We're talking about Mohr's circle and how it completely decodes geotechnical slope stability.
So, think about this macro-level problem we face all the time. Before we can safely build a massive highway, lay the foundation for a soaring skyscraper, or carve out a deep mine, we have to understand the invisible forces at play. How do we predict when thousands of tons of earth and rock are just going to suddenly give way? To figure that out, we're going to walk through the threat of shear failure, meet the brilliant Christian Otto Mohr, zoom into the 2D stress element, draw Mohr's circle, apply the Mohr-Coulomb criterion, and finally look at real-world slope stability and design.
Section 1. The threat of shear failure and why the Earth actually gives way.
Let's start with what physically happens when a hillside collapses. Unlike steel or wood, soils have virtually zero tensile strength. You literally can't stretch dirt. Because of that, soils almost always fail in shear. As our sources point out, this failure happens through the sliding and rotation of soil particles against each other, which is basically tearing along a plane when opposing forces push past one another. And the resistance to that sliding, that shear strength, boils down to two main things. First, we've got cohesion, represented by the letter C, which acts like a natural cement, binding clay soils or intact rocks together. Second, there's the friction angle, represented by the Greek letter phi. This is all about the physical interlock, the grinding friction of larger particles like sand and gravel. If you want to stop a landslide, you're relying entirely on these two properties holding the line.
Section 2. Meet Christian Otto Mohr, the engineer behind the circle.
So who gave us the ultimate decoder ring for these forces? A 19th century German engineer named Christian Otto Mohr. He actually started his career designing railroad bridges using early steel trusses. Working with those massive, heavy loads sparked a lifelong obsession with the strength of materials. Eventually, in 1882, he published a brilliantly simple graphical method. He figured out how to visually map 3D stress without making engineers rely on blindingly complex calculus. A real game changer.
Section 3. The 2D stress element. Time to zoom in to the micro level.
To understand how Mohr actually mapped this stress, we need to take a magnifying glass and zoom way down from a giant hill to a tiny microscopic square of soil. We do this by assuming plane stress. It's a handy simplification where an incredibly thin element has all its stresses acting in one single plane. Making this assumption lets us analyze internal forces using a simple 2D stress element that represents just one single point inside the ground.
Look at the components acting on this microscopic square. You've got normal stress either pulling it apart in tension or squashing it in compression. Then you've got shear stress sliding along the X and Y faces. But here's the kicker. If you physically rotate this little element by an angle theta, the overall stress state of that dirt doesn't change at all, but the normal and shear components shift depending on your new viewing angle. So a block of soil might look perfectly stable from one angle, but could be completely failing in shear along a hidden diagonal plane. Sneaky, right?
Section 4. Drawing Mohr's circle and visualizing that stress transformation.
Instead of churning through tedious equations to track those shifting stresses on every possible angled plane, Mohr gave us this beautifully simple geometrical recipe. Step 1. Plot the normal and shear stress on the X face. Step 2. Plot the normal and shear stress on the Y face. Step 3. Draw a straight line connecting those 2 points to form your diameter. And Step 4. Just draw the circle. By plotting these coordinates, where the horizontal axis is normal stress and the vertical axis is shear stress, you can instantly visually determine the exact stress state for absolutely any orientation. Now, the absolute most crucial part of this is finding what we call the principal stresses. These are located at the far left and far right edges of your circle. Notice how at those specific points the circle crosses the horizontal axis? That means the shear stress there is exactly 0. Pinpointing these maximum and minimum normal stresses is an absolutely essential first step in predicting when your material is going to fail. Oh, and when you're using this tool, you have to remember the golden 2-to-1 rule. A physical rotation of an angle theta on your actual microscopic soil element corresponds to a rotation of 2 theta on Mohr's circle. It's this wild little quirk of geometry that perfectly maps to the real-world physics.
Section 5. The Mohr-Coulomb criterion, or exactly where the soil breaks.
Now we combine Mohr's graphical circle with Coulomb's hypothesis to figure out exactly when our soil is going to surrender to the load. The Mohr-Coulomb equation is literally the heart of geotechnical engineering. It perfectly illustrates how shear strength, the tau symbol, is a direct mathematical combination of the soil's inherent cohesion and its load-dependent friction angle. Mohr's circle tells us what stresses are present, and the Coulomb criterion tells us the absolute maximum threshold that dirt can take before it slides.
While it does have a few limitations when you get into really highly complex rock masses, this elasto-brittle plastic model is incredibly well suited for evaluating the stability of mining and geotechnical problems. And by elasto-brittle plastic, I mean it accounts for how materials stretch, snap, or permanently deform. It effectively models soils and gravels, evaluates both peak and residual strength, and even accounts for volume dilation, which is just a fancy way of saying it predicts how soil expands when it breaks.
Section 6. Slope Stability and Design. Applying math to save lives.
Let's zoom back out to the macro level. Today, engineers aren't exactly sitting around drawing these circles by hand on drafting paper. Instead, they take the Mohr-Coulomb failure criterion data, specifically those peak cohesion and friction angles we just talked about, and input them directly into advanced simulation software like Rock Science. The software then uses those inputs to simulate incredibly complex stress paths for drained and undrained triaxial compression tests. Basically, it's mathematically predicting how water pressure, volumetric strain, and massive construction loads are going to impact the material long before a single shovel ever hits the dirt.
And the result? You get these stunning 3D evaluations of a soil's yield surface, the exact boundary where the earth will fail. By clearly understanding this boundary in a 3D stress space, engineers can confidently design the retaining walls and deep foundations that safely hold back thousands of tons of earth.
It's honestly incredible to think about. Preventing massive macroscopic disasters literally comes down to plotting the simple 2D geometry of stress on a tiny microscopic grain of soil. It definitely leaves you wondering, what else in our built world relies entirely on hidden mechanics just like this?